to take you to a journey through the science around protoplanetary disks. So what do we know about them as the kind of cradles for exoplanet formation? And I will then also later in the talk talk about new JWST observations and what they will tell us. So when you think about protoplanetary disks, probably you have images like this in your head. So these are ARMA observations from interferometry in the large Atacama Desert in Chile. So everybody associates protoplanetary disks with these kind of images. So you see these rings. But I want to say that this is actually a very peculiar way to look at protoplanetary disks. This is not telling you anything about the gas. It's also not telling you about the majority of the grains. What you see here is the distribution of large grains, so the millimeter opacity carriers. And when you look at other wavelengths, for example, here's a scattered light image done with sphere, with polarimetry. You see the shape is now completely different. So there's a third dimension, whereas in ARMA, everything looks completely paper flat. And this is because the grains are actually, the small grains are actually stirred up, and then they scatter the light from higher layers. So you see a kind of car wheel here, whereas in ARMA, you really only see the midplane. And these three images are actually all to the same scale. The only difference between these two images here is that this is high resolution interferometry focusing on the inner parts, and there you see these rings. But if you have a more global view, you see that these things are actually very extended. So in this case, it's up to 400 AU is the radius that we can still trace the dust. And in the gas, it's actually similar in this case. But this is actually one of the best objects we have. This is IM Lupi. So it's a very large, very bright disk, and it's a very beautiful one as well. Now, when you look at the gas, it's actually even more different. So here again is an ARMA image of a protoplanetary disk with this number here. And in the gas, first of all, it looks even bigger normally in the gas. And then again, it's not clearly a disk. It's more like, I would say this is a lorry wheel. Yeah? So it's even bigger, and it's very obvious. When you think about, you look from here inside, there's a central star is here, and this is where you look. So you can look from here. So the axis is here. So it's very big, very extended, also vertically very extended. Now, interesting, I get some scribbles here on the slide. Here we are looking at different objects, and this is in dust with ARMA, and this is in gas, also with ARMA. And there you see that the dust and the gas are doing something quite dissimilar. So they can be quite different. And it's also not so easy to say general things. So each object can be quite different. And even when you look at the same object now in different gas lines, the appearance is different. So that obviously probes the chemistry. So here you see HDN molecules, here you see T2H molecules, etc. And sometimes the gas structure mimics the ring structure, but in many, many cases, it's not the case. So the gas is more, it's differently distributed. So it's not necessarily the same as the ARMA millimeter images that we know from the continuum. A little bit on star formation and disk evolution. If you don't know this, so this is a popular introductory slide. So this is our basic picture how stars and planets form. So you somehow in the course of the molecular clouds, you start contracting, and there's a little bit of rotation, but as the spatial scales here shrink by some orders of magnitude, the thing spins up because of angular momentum conservation. And then you form what is called a protoplanetary disk. So in this class 0 phase, there's actually the star is not visible yet. So there's only kind of indirect proofs that there is a star already. It's in the formation of the star. It's not very bright at all. And you mostly see just the rotating gas, but there are first indications of rotation. And then in class 1, there's clearly the star pops up and the disk becomes very clear, but there's still a lot of remaining stuff around. You also have winds and jets that escape, take away some of the angular momentum. And then in class 2 and class 3 is kind of where we expect most of the planet formation to form. So in this early stages, it's just too short a little to really form planets. So maybe it starts already here and then continues in class 2. And then what is called class 3 here is when the gas starts to disperse and the disk is also truncated maybe from the inside and from the outside. And in the end, you end up with a planetary system as we know it. Now I will talk about a little bit about physics and chemistry because I'm more like a theoretical modeler. I'm not an observer. And so here in this sketch on the left-hand side, you can see some of the processes that the dust is doing. So this is really important. So you have some turbulence, you have ice lines, dust is settling, etc. On the right-hand side, you have processes that are important for the gas phase. So only in the midplane, you have ice formation, and then you have this interesting layer structure where the gas from very cold gets actually very hot. And it is these kind of intermittent layers that we can observe with different telescopes at different wavelengths. And JWST is taking its part here on the inner part and in the inner disk, as I will show later. So how do we all model this? In the end, we want to understand our observations. And this, what I'm representing here are so-called thermo-chemical disk models. So there's no hydrodynamics here, but it's rather that we put the disk as we think it is. For example, we have to assume some kind of two-dimensional gas density structure. And then we also have to put some kind of dust properties, so the dust size distribution, the material composition. We have to apply some theory concerning gravitational settling. That is very important. So, you know, how strongly are the bigger grains concentrated in the midplane? And then you also have to think about your star. So the star illuminates the disk, and it does so not only with an optical radiation, but in particular also with UV, X-rays, and so these are stellar energetic particles. So these will have an impact on the chemical processes and also on the temperature of your disk. And so young stars are known to be, for example, quite strong X-ray emitters, and that plays a role. Then you can also put your disk into an environmental place. So you can play with some of the background parameters that we have concerning interstellar irradiation. So there's interstellar UV, there's interstellar infrared radiation, maybe in a dense cluster, and there's cosmic rays. And then there's a lot of options, of course, what we want to do. In principle, we have these 4 pillars. So ProDiMo is called the protoplanetary disk model. I would rather say ProDiMo than ProDiMo because it's disk and not disk. Okay, so we have chemistry, we have radiative transfer, there's hydrostatics. So there's a little bit of theory also going into the 2D structure, and there's heating and cooling. And this is kind of what we are trying to solve. I want to show now a little bit of basic concepts. So when it comes to the vertical structure of the gas and the dust, what do we assume there as physicists? So basically for the gas, we have 3 things. We have centrifugal forces, pressure gradients, and gravity. And in the radial direction, these 3 things, so the centrifugal force is either balanced by gravity, and for the gas, there's also a little bit of this term, which is actually very important for the dust dynamics. But if you're only interested in the gas structure, that's not so important. So we neglect this term here now. For the vertical direction, well, there's no centrifugal force, but then you only have the balance between gravity and vertical pressure gradient. And here are some equations that is actually very basic, so you can solve this with pen and paper. From here, given the gravitational potential, and then you end up with this equation here. So that tells us how quickly the vertical the pressure decreases in the vertical direction. And you can solve this, and this gives you a Gaussian distribution. So this is here. So the pressure as function of z. So z is now the coordinate from the midplane upwards. And so it's a midplane pressure, and then comes a Gaussian. But with z square over scale height square. And if you know your temperature and mean molecular weight, then, or if this is constant, then you can solve it this way, and then there is a scale height. However, if these two things are not constant, so this is the pressure as function of z, and this is the mean molecular weight, then actually there's no such solution, and a scale height doesn't really exist. And this graph shows this a little bit. So here we have the pressure in log units, and here's the midplane at 0. And then here we go up, and then here we go down. And of course, it's symmetric. And then you see, okay, in the central part, actually where the temperature here and the mu, so the mean molecular weight, is constant. Yes, indeed, we get a Gaussian. But then the temperature actually increases because you're leaving the shadow, and it becomes very hot. And at the same time, the chemistry does something funny. So it ionizes, or dissociates and ionizes. And that changes things. And then you end up with actually quite a different distribution. When it comes to dust, the basic principle here is that you have two things that balance each other. It's mixing and settling. So kind of stirring by turbulence versus gravitational settling. So in the co-rotating frame, there is only a gravitational component downwards that forces all grains to settle down to the midplane. But then this is balanced by upstirring. So if there's some kind of turbulence, then these things will be whirled up all the time, and you get a balance. And that's what the settled dust distribution then is. And so, yeah, this is actually quite a beautiful expression here. So you see that the change of the gas to dust ratio, F is a normalized dust size distribution function. So we have different sizes of particles. And for each size, the parameters are slightly different because the drift velocity, so the vertical settling velocity, depends on the size. So if this is well stirred, so if D, the mixing coefficient or diffusion coefficient by eddy diffusion, is really large, then this is kind of 0, and you get perfect coupling between gas and dust. But depending on size, at some point it will become important. And then it will strongly, all of a sudden, you will lose the grains of a certain size. And this is kind of visualized here. So again, we are now only using constant temperature and molecular weight. So the gas is distributed with a Gaussian. And you see that in this model here, with a certain theory, then the small grains are perfectly coupled to the gas. So they mirror what the gas is doing, but the larger grains then start to settle towards the midplane. But the more modern formulation of this then would predict that even the small grains are not following the gas perfectly, but they soon will also deviate from the gas. And this is kind of shown here. So here we have Z over R, so it's the relative height. So the Z coordinate divided by the R coordinate. And this is log radius. And so this is kind of cut through the disk. And we see here the gas distribution in terms of particles per cubic centimeter. And with this old formulation concerning for this case, you see that the dust is a little bit more concentrated towards the midplane. But according to a new formulation with the same turbulence parameter, it's much more settled. And this is actually one of the keys, I think, what we need in order to understand the JWST observations. I will show that later. Next item is radiative transfer. So this is, it's one of the biggest program parts. So it's the module where you'd have a solution of the radiative transfer equation. And if you know a little bit of astronomy or astrophysics, I hope that you have seen this equation maybe already before. So this is radiative transfer equation. Here are the source terms. And I'm talking now only about the dust. So forget about the gas. It doesn't have a big opacity. So most of the opacity is in the grains. And then you can formulate your problem with this source function. In this case, it's isotropic scattering assumed. So the mean intensity actually comes in here. And you also need to know the dust temperature. And then you know your source function, and then you can solve this. And then you can actually look for the dust energy balance. So this would be the dust, if it's in perfect radiative equilibrium, then this equation is just zero. So heating and cooling is the same thing. So you have this is the heating term, so the absorption of light, and here we have the integrated emission of light. In equilibrium, this must be the same. And then there's also possibly other heating and cooling things. And in particular, we have the viscous heating. And so you can, now you see the structure of these equations, that only when you've done this once, you can actually determine the dust temperature. When you're done, then you can solve for the dust temperature that solves this equation. And then you have to go back and do it again. So it's an iterative problem. It's called an integral differential equation. So in the radiative transfer, you have to be very careful with your sources. So there's a star. So we use tabulated stellar spectra. And then normally some assumptions or some measurements about what is going on in the UV, because these are young stars and they have extra UV. They have chromospheric UV. They have accretion shocks. So this must be put into the models in some ways. And there also can be X-rays. And then you have the disk is also irradiated in this model isotropically from the environment. And then you can solve this, and then you get actually your temperature and your mean intensities, which you need later on. So here are some of the details. I think I skipped that. Now, our method is actually not the Monte Carlo method, which is the leading method in this field, but this is a Bray-based method. But we have benchmarked it very carefully and developed it over a long time. And here's a comparison between what we get. So in blue is ProDiMo. And this is one of the radiative transfer codes, MC-FOST. Here's the colors are reversed, unfortunately. So here's black is ProDiMo, and MC-Max is another Monte Carlo program. And what you see here is the temperature now in Kelvin for certain selected radii plotted over Z. So here's negative, here's positive. So you go into the shadow and then you go out of the shadow again. And then you see in this kind of passive disk where there's no viscosity assumed, you get very soon into a shadow. And there the temperatures are very low. And there you can form the ices, etc. But then as you go out of the shadow, when the disk becomes optically thin in the radial direction, then the temperature increases. And that is a kind of optically thin temperature limit. However, if you have an active disk, so where viscous processes are still important in the center of the disk, then there is an additional heating. And here we have the interesting case that, this radiation or the energy that is accumulating there from the viscosity cannot get rid easily, because everything is optically super thick. From the midplane, you have optical depth like 1,000 or 100 or so. And then the only way to do that is actually by diffusive radiative transfer. So you have to make an inverse temperature gradient in order to transport your heat upwards. And then you can lose it when it becomes optically thin. And that means that the temperature actually increases towards the midplane. And this is, I think, very important effect. It's well known for the ice lines, etc. So when you want to connect this to planet formation, this is an important effect. And recently, there is a paper out about so-called calcium-aluminium rich inclusions, because this effect that I just showed opens an interesting idea how to form the CIAs. So we saw that the temperatures can become actually very large, close to the star in the midplane. And what happens physically is that in this case, the silicates might actually evaporate. but only so far, because in the end, when you evaporate the grains, then you also lose the opacity, and then there's no of this effect that it kind of piles up in the middle, but it can easily be transported upwards, and this makes a perfect temperature thermostat. So you get a temperature regulated, and then everything only depends kind of on the accretion rate. And so in very early phases where the accretion rate is still very high, so how much mass is actually flowing through the disk and towards the star or from the cloud, that leads to a region here where the silicates are all gone, and you only have the aluminum, calcium, and titanium oxides that are still stable, because they alone don't make it optically thick. And if you now combine this with this scenario 2, that actually you feed the disk from the cloud fairly close to the star, then you get an outward motion. And then you get actually the formation of these seeds of CIA. And later on, when they move, they are then only covered by this matrix, which is called the silicate matrix. So this actually gives us a very nice idea how these how these CIA-rich inclusions are formed. Whoops, what is this? Oh, sorry, I missed, yeah, okay. Yeah, okay, chemistry. That's the third pillar of ProDiMo. So what we do is we are solving a chemical rate network. You can formulate this like this. So here you have the number densities of your species, and these are production rates and loss rates. And there might be also some mixing rates. So this would be the divergence of a diffusive flux. And typically we are talking about, say, a couple of hundred species, couple of thousand reactions. And there are several ways to solve this. So one quick and dirty thing is you just look for the kinetic chemical equilibrium. So you forget about the time dependence and just solve all my particle densities, where is the production equal to the destruction. Or you can do it time dependently, or you can do it actually, for example, including some reaction diffusion, some diffusion rates. That's now a very complicated partial differential equation system, which is called a reaction diffusion system. But generally, you have to know all these rate constants here. So the rates, for example, of photo rates is just a constant times your particle density. And this K here is, for example, then this is where the radiation field goes in. And this is the photoionization, photodissociation rates. Then you have the normal two-body reactions, so say the neutral-neutral reactions or neutral ion-neutral reactions, etc. So where molecule A collides with the molecule B and gives you a molecule D and E. Then there's also thermomolecular reactions, where you combine three of them, where you go through an activated complex, and then a third body, which is called M, collides with this activated complex and stabilizes the results. And so the art here is really to gather all these interesting processes. So all the rate constants must come from somewhere. And we are mostly using the UMIS 2022 database, but we can also use KIDA. We have some photocross sections from the Leiden database, etc., and some other ideas. I don't want to explain everything here, but basically here in this K2, this is a typical Arrhenius law, where you need your parameters alpha, beta, gamma. This is coming from the UMIS database. If you think about these kind of rates or photo rates, then you need to know the cross sections, the photo cross sections of your molecules. And the results are then your molecular abundances. And I just want to highlight here that in order to solve the chemistry, we need to know the temperature and the radiation field. Now, the radiation field comes from the radiative transfer I just explained. This is why we are doing the radiative transfer in the first point. But where does the temperature come from? You will see. Here's an idea of a chemical and rate network. So what it means, so here we have X-ray irradiation, kind of interesting region for JWST. So where X-rays kind of ionize hydrogen and they ionize also helium, and the helium, for example, then attacks the basic molecules like CO and N2, and then you activate, you have all of a sudden you have some electrons, you have some atoms, and they then continue to react with each other, and for example, giving us then some of the HCN and C2H2 molecules, which are normally not that abundant, but when you irradiate them with X-rays, you get them. And this is actually also very important. Okay, heating and cooling. I think in interest of time, I will skip a little bit here. Basically, you need to think about all these processes have an imprint of your internal energy, and you have to quantify that. So all the processes will I get some interesting scribbles here on my screen. And you have to balance all them, and that's the way you determine the gas temperature. Yeah, I will skip a little bit about this because we are running a little late. Now, this is the basic structure now of ProDiMo. So you see these 4 pillars, and you have to solve everything. Yeah? So the hydrostatic structure, then you can do the radiative transfer. There's this internal iteration because you need to solve the scattering problems. That's what I said. It's an integral differential equation. And then you solve the chemistry and heat thermal balance. That gives you the gas temperature. And then you can renew the vertical disk structure, and then you have to go on like this. So this is a very complicated, so if you switch on everything, yeah, this is a very complicated thing. But for example, what we often do is we just fix the disk structure. We are not solving a hydrostatic equilibrium, but we just put a parametric disk structure, and then you only do everything once, and then it's kind of relatively fast. So you can calculate a decent disk model within an hour, roughly. And then you get the results. So here, this is the gas density that is assumed in this case. And then you get all your concentrations of all your molecules. You get the dust temperature structure, and you get the gas temperature structure. And these are then used in order to calculate a lot of observations. So here's an example of an SED, so a spectral energy distribution. On top of that, you see all the line fluxes calculated. So the lines are all calculated anyway for the heating and cooling. And this is kind of a simple prediction of how strong these lines should be. We have continuum images, we have channel maps, we can calculate visibilities. And then for ALMA in particular, we can do these velocity profiles or maps, molecular maps, how they would look like with ALMA. And then for JWST, this is a new thing. So this is the FLITS, the fast line transfer by Michael Min. So we can use the ProDiMo structure and run this kind of line transfer, which gives us tens of thousands of lines in one go, and we can create an infrared spectrum. And that brings me to my last part of this talk, which is the JWST observations. So here, this is all since about 2023. So the first papers came out in 2023, at the end of 2023, about EX Loopy. And then, for example, this here is what is shown, what the observations, how they look like. So this is done with the MIRI instrument. So this is a mid-infrared spectrometer, has a resolution of about 3000. And with this, you can now really see all these kind of interesting lines. This is after continuum subtraction. And here they put together a very simple model, which is called a slab model. So you don't really have a disk in this model. You just take a box, put some molecules in it with a certain temperature, and then you calculate what would come out at this given column density. Now, this is more the ordinary T-Tauri disks here. They look like this. So they have a lot of water lines, and there's also CO, which you can't see here. And then they have CO2, etc. But then there's this new class of VLMS disks. So these are very low mass star disks. It's kind of M stars, early M stars. And some of them, or most of them, I would say, are actually showing a very different spectrum, which is kind of breathtaking. They are showing only hydrocarbon molecules. So all these molecules are hydrocarbon molecules. There's a little bit of CO2 though, but for example, no water. So this tells us immediately that we are looking at a completely different chemistry. When we look at the analysis of these data, so these are the simple SLAP model analysis, you see, well, you get some really high column densities of these molecules. So of the order of 10 to 60, maybe 10 to 18 or 10 to 19 molecules per square centimeter. And this is kind of over the dust. And this now connects to what I said, that it's important for us to settle the grains. If we wouldn't do that in the models, we would not get these kind of column densities. And the other interesting thing is concerning the radii. So they can estimate how big is the emission area from this modeling. And it's very small. So it's of the order of 0.1 AU. Sometimes it's maybe up to 1 AU for a little brighter object maybe. But this is very small. So JWST probes the really innermost disk. And now this is our paper from 2022, and I'm very proud that it was possible to actually now use a full 2D ProDiMo model and to fit it to a given JWST spectrum. And this is what came out. So the disk structure was kind of parameterized. And this is the outcome of the model. We had 17 free parameters for this fitting exercise. We didn't touch the C/O ratio, so this was fixed to the normal interstellar value. And then there was just a genetic fitting algorithm that, within a few hundred generations, it leads to a fit. So it's not at all something like MCMC, but only we can, well, one model takes an hour or so. So altogether, this was required like 10 to 5 CPU hours in order to run that. And this is the fit that came out. So it's not only that we can fit the molecular lines. So here you see the CO, the water lines, and then there's C2H2. HCN is a little weak still, but it's not too bad. And CO2 is also there. And we can also, at the same time, we fitted the SED of this object. So from my knowledge, this is the first time that such an attempt was successful. So we are using the super complicated 2D structure, which has consistent temperatures, consistent molecular concentrations. We put that through flits, and out comes a spectrum that can be compared to a JWST spectrum. Now, concerning this other class of VLMS, so Jayati Kanva, who was a PhD student, worked on something similar, but we are not quite there yet, I would say. So what she did is she said, okay, we need these kind of carbon-rich inner disks. So she put the C/O ratio to 100. And still the CO lines are, say, too over-predicted. So it seems that we need really a very lot of carbon or very little oxygen. Both works. And then these hydrocarbon molecules form a so-called quasi-continuum. So this is not continuum here. This is after continuum subtraction. So this is actually what is only molecular emission. And because of the scale heights, because of the column densities, they are so large that even the molecules become optically thick already, even between the lines, so to speak. And this is what we could show also with ProDiMo. So this is a ProDiMo model. Its fit is not perfect, but I think we have more or less a good result. That brings me to the end of this talk. So you can imagine I talked a little bit about ARMA and JWST, but in general, you will, with different instruments, you're probing very different regions in the disk. With ARMA, you are probing the outer part. With JWST, we have now a perfect instrument to probe this molecular chemistry in the inner disk where the planets are forming. And so in principle, one has to combine all these things. Also the continuum, so this is only for the lines, but you also have to think about the continuum, the disk shape. So for these T-Tauri stars, they are just very different from these low-mass stars or M stars, but we need really high column densities in order to interpret these observations. And this is only possible if the dust is either very large and transparent, That's a possibility, or entirely missing. We can't really say. But we have to have a lot of gas over the dust. And here, the other idea is that we have just intense dust settling that also works. Interestingly enough, we need X-rays in order to produce a lot of C2H2 and HCN, what we see in normal T-Tauri stars. And we know that T-Tauri stars are strong X-ray emitters, so that is actually a nice explanation. And more generally speaking, ProDiMo is a versatile tool to study disk physics and chemistry. And you are very welcome actually to use it. So you talk to me if you want to model disk. And what I want to also mention in the end is that there are 2 open PhD positions at the moment in Graz. And one would be with me actually about something different, about the Venus atmosphere. This will be about the simulation of deuterium and H2O to water. Together with my colleague Helmut Lemmer. Okay, thank you very much for your attention.